Happy Monday afternoon. Then look at the shape of a graph. We're going to redefine increasing and decreasing from how it was defined in pre-calc. If f prime of x is greater than 0 for all x in an open interval AB, we say that f is increasing over the closed interval A to B. And if f prime is negative, we say it's decreasing. Which leads into the first derivative test, which is a test for extrema. F is continuous over an interval I containing a critical point C. If F is differentiable over I, except possibly at C, then F of C will satisfy one of the following. F of C is going to be a local max if F prime changes sign from positive when x is less than C to negative when x is greater than C. Right, so when the function switches from increasing to decreasing at a point, that point results in a maximum. If F prime changes sign from negative when x is less than C to positive when x is greater than C, f of C is a local min. And so the function changes from decreasing to increasing. You get a minimum. And if f prime doesn't change sign, so it has the same sign for x less than C and x greater than C, then f of C is not a local extremum. concavity, we're going to have a function that is differentiable over an open interval I. If f prime is increasing, we say that f is concave up or convex. If f prime is decreasing, we say that f is concave down or just simply concave over I. And then the test for concavity is essentially just testing f prime. When is it increasing versus decreasing? So f double prime is greater than 0. We say that f is concave up. F double prime less than 0, f is concave down. And if f is continuous at A and f changes concavity at A, that point A, f of A, is a point of inflection or inflection point.
By this definition, would all extrema be inflection? No.
Actually, extrema aren't ever going to be inflection points.
So concavity changes when our base function goes from increasing to decreasing, right? No?
Concavity changes when the derivative switches increasing to decreasing, or decreasing to increasing.
Okay.
The inflection points would be extrema of the derivative. Second derivative test, suppose f prime of c is 0 and f double prime is continuous over an interval containing c. If f double prime of c is greater than 0, F has a relative minimum at C, and if F double prime of C is less than 0, then F has a relative maximum at C. If F double prime is 0, the test is inconclusive. Second derivative test has a corollary, which states if C is the only such value, such that F prime C is 0 in the interval, then it's no longer a relative extrema, it's an absolute extrema. So we're going to list intervals where each function is increasing and decreasing, convex and concave. We'll also list out all the extrema and inflection points. First thing we need is F prime. Let's also find F double prime, why not? List that out. We'll start by analyzing F prime. Is there anywhere that F prime is undefined?
No.
Now we just set it equal to 0. Should easily see that's going to lead to x being 1. Is that in the domain of F?
You weren't given a domain, so I assume it's all real numbers, correct?
You're not explicitly given a domain,
Not explicitly.
but there is implicitly a domain that is given. And yes, it is all real numbers.
Okay.
So yes, this is in the domain. That's a critical point. So now set up the test intervals. Right, because what we're doing is we're essentially solving an inequality. We're solving two inequalities, actually. We're solving when f prime is less than 0, when f prime is greater than 0. Remember, the first thing you did when solving inequalities was to find all of your breakpoints, which are, of course, where the function does not exist or is 0. Then you wanted to set up your chart of intervals with the signs, and then the sign that you take depends on the inequality. That's essentially what we're doing here. We're splitting our domain at the critical points. In this case, it's 1. So you have 2 test intervals. Actually, I think we leave something else. I'm going to include a row, at least for now, of the test point. We'll see how long I do that for. Pick any point within the interval. Zero is the easiest point. Pick a point in the second interval. 10 is also, generally speaking, an easy one to work with. It doesn't matter, you can use any point you want. Plug each point into the derivative and determine its sign. F prime of 0 is negative. F prime of 10 is positive. I'll worry about interpreting that chart later. Now let's do the exact same game with F double prime. Is there anywhere that F double prime of X is undefined?
No.
F double prime of X equals 0 is a contradiction. F double prime of X will not equal 0. That means that F prime has no critical points. So we only have one interval to consider, and that's the domain, all your numbers. If test point 0, plug it into F double prime. Is it positive or negative? Now for the interpretations. Increasing whenever the first derivative is positive. So we're increasing on the interval 1 to infinity. Decreasing whenever the first derivative is negative, minus infinity to 1. Convex when the second derivative is positive. Concave when the second derivative is negative. Listing extrema and points of inflection. Max when it switches from increasing to decreasing. Doesn't. So there's no max. Min when it switches from decreasing to increasing. At 1. Plug 1 into f of x. What is f of 1? Zero. So relative min at 1, 0. Flexion points are anywhere the concavity switches. Does concavity switch? No. So there's no inflection points. The analysis is complete. What is f prime? What is f double prime? Is there anywhere f prime is undefined? For f prime to be 0, 2x squared minus 2x plus 3 would have to be 0. Discriminant. B squared minus 4ac. 4 minus 24. Discriminant is negative, which means there's no solution. So f prime equals 0 is a contradiction. It means there's no critical points. Anywhere that f double prime is undefined, f double prime equals 0 means that 2x minus 1 is 0. So what's x?
1/2.
It's 1/2 in the domain of f.
Yes.
Call it c prime to represent critical point of the derivative. And so the derivative has a critical point. F prime had no critical points. Since the domain of f is all real numbers, we have a single interval. Choose 0 as your test point. Why not? What's f prime of 0? Positive, right? F prime did have a critical point. We're going to split the domain of f at that point. Choose the test point in each interval, then determine the sign of f double prime. At 0, it's negative. At 10, it's positive. Increasing when the derivative is positive. Decreasing when the derivative is negative. Increases everywhere, decreases nowhere. Convex when the second derivative is positive. Concave when it's negative. Does f prime change sign? means there's no extremity. Does F double prime change sign?
Does.
So we have an inflection point. Change of sign at 1/2. What's and there's the analysis. What's F prime? What's F double prime? So anywhere that F prime is undefined. Now set F prime equal to 0. How would you solve that? Hmm? Okay, synthetic division, what are you dividing by? Huh? factor by grouping. How many critical points are there? What are they?
2.
Working out of room. Is there anywhere f double prime is undefined? Set it equal to 0. X squared minus 4x minus 1 equals 0. 16 minus 12 is positive. We have solutions. We have distinct solutions. Neutral weight. Can that be factored nicely? Nope. So we have to use what?
A quadratic formula.
Negative b plus or minus the square root of b squared minus 4ac. It's actually plus 12 all over 2a. And 12, 28. Root 28 is 2 root 7. C1 prime. Two minus root 7 over 3. C2 prime is 2 plus root 7 over 3. So start with the sign table for f prime. How many critical points did we have? What were they? What was the domain of f? Split the domain at the critical points. Gives us 4 intervals. Choose your test points. That one's nice. That one's really nice. That one's nice. Yeah, that third one's not so nice. Go back to f prime. Negative 10. Is positive. Zero. 3/2. Making this harder than it needs to be. 3/2 minus 2 is what? Negative, isn't it? 3/2 squared is larger than 1. That's negative times positive, which is negative. But then I factor out a negative. So negative times negative is positive. F prime is positive at 3/2. And what about 10? Negative. There's our sign chart for f prime. Sign chart for f double prime. We have 2 points. Split the domain of f at those 2 points gives us 3 test intervals. There's our 3 test intervals. Pick a point from each interval. Is 0 in that middle interval? It is. That makes that so easy. So go back to f double prime. At negative 10, positive or negative? Well, I'm going to look here again. It's negative. At 0. Clearly positive. And then at 10, be negative again. Increasing whenever f prime is positive. Minus infinity to minus 1 and 1 to 2. Decreases whenever f prime is negative. Convex when the second derivative is positive. Concave wherever it is negative. Do we have extrema?
Yeah, we do.
So whenever the first derivative changes sign, we're going to have an extrema. Do we have maxima?
We do.
How many?
We have 2 of them.
Do we have minima? How many?
Just 1.
Where's the max? What's f of negative 1? $21. f of 2 ends up being -6. Where's the minimum? And f of 1? -11. Do we have inflection points? How many? Two. What is f of that? That's what I got. I'm not entirely convinced that's correct. Close. Should be 80√7 instead of 80√8. Those are the two inflection points. Trig function would be fun. What's f prime? What's f double prime? You said that? Is there anywhere f prime is undefined? What's cosine of pi? Secant pi with any 1 over negative 1.
It has to be pi over 2, right? Or pi over 2, but those are the boundaries of our thing, and they're not included. So in this range, there's nowhere undefined. That interval does not include the values on it on Z-list.
What values does it include?
Well, it's not the not the brackets about the sharp corners.
I agree.
So it doesn't include 3 pi over 2 or negative 3 pi over 2.
I agree.
And negative 3 pi over 2 is the same thing as pi over 2. Right? Am I misremembering this?
I agree. Isn't pi over 2 between negative 3 pi over 2 and 3 pi over 2 though?
Oh. Okay, pi over 2 then.
Shouldn't, because you were right, just for the wrong reason. It's defined everywhere. Because the domain of secant is everything except for odd multiples of pi over 2. Which means the only place the derivative is undefined isn't even in our domain to begin with. So it's defined everywhere.
So do all the inverse functions have domains like that
Inverse functions,
in the reciprocal things, those?
they're going to have restricted domains, yes.
Okay, so it's not something we
So you
have
have
to worry
to
about.
keep an eye on it. F prime is 0. Can secant ever be 0? No. Can tangent ever be 0? Tangent can be 0. Which means you have to worry about tangent of x being 0. Where's tangent 0?
Every multiple of pi.
Multiples of pi, because it's ever assigned as 0. But we're in a restricted interval. So we don't have an infinite number of them, otherwise we would. So now just look at minus 3 pi over 2 to 3 pi over 2. At what points in that interval is tangent 0? Those are the critical points.
I think we just have 1 pi and 0 pi.
Give us one.
And negative 1 pi.
Negative pi, 0, and pi are the 3 critical points. Is there anywhere f double prime is undefined? Again, it would just be undefined at points that aren't even in our domain.
Are we just going to have the exact same zeros here?
Are we?
I'm going to say we are.
If f double prime is 0, if I've got a secant, we left with secant squared plus tangent squared. We already know that secant can't be 0. Can secant squared plus tangent squared ever be 0?
Well, if that can't ever be 0 and we're adding it to something else, well, then that something else doesn't matter, so no, it can't be 0.
If what equals each other? If they equal each other, isn't just 2 times the 1?
I mean, so with opposite signs,
Is that possible? No? Then you're saying square is negative, which it can't be. Which means it's never 0. Oh boy, this is gonna be fun. So we have to split our interval at the critical points. There's one. There's one. Remember, you have to exclude minus pi over 2 because it's not in the domain of secant. Right, so the interval, yes, is minus 3 pi over 2 to 3 pi over 2. However, because of the domain of secant, that interval itself is actually split. All right, so there's the next critical point. But secant's undefined at pi over 2. Then we go pi over 2 to pi. And finally, and now here, test points don't matter. So all I have to do is worry about how does secant and tangent behave on each interval. If you know your trig, it's very easy. Same thing here. The points don't actually matter. If you know how the trig functions behave on each interval, this is extremely easy. You can write out the intervals of increasing, decreasing, the intervals of convex, concave. Are there points of inflection? Sure. That's true. Where's it change in concavity? What points? Are they in our domain? Secant's undefined at those 2 points, which means there are no inflection points. Here's how you could also tell. Did we list any critical points of the first derivative? No, which means there can't be inflection points. So that's a trick. Because those points are not included, they cannot be inflection points. It would be the same argument with extrema if your sign changed at a point not in your domain. Then that wouldn't be an extrema. In this case, I don't think that happens. Right? Because negative pi is included, 0 is included, and so is pi. So here you would have 3 extreme values. You would have what? 2 maxima and a minimum. We have one thing left to do before the exam, and that's optimization.